Hello class. In this video, we're going to look at a few more aspects of branching statements in Java. Starting out, we're going to look at the switch statement. Now, if you remember from the prior videos, we looked at the if and else statements where we could make decisions and either do something or not depending on a condition. If we wanted to look at multiple conditions, we would need multiple if statements to be able to account for all the possible combinations. Well, the switch statement allows us to do that looking at multiple discrete values without the need for multiple statements. So we're going to take a look at the switch statement and see how we can use that. And we'll implement a couple of different ideas, starting with the flipping of a coin and then perhaps the rolling of a single die. So we have a choice of 2 possible values or 6 possible values. So I've gone ahead and I've opened up a new tab where we have our lab. And we're going to take a look at, first we're going to have to create some random numbers. So why don't we import our random number generator. Import java.util.random. Import the random number class. Need another slash here. Let's get that out there in front. And we'll create 2 integer variables. We're going to create a, first one we'll create is the dice roll. We'll call it dice roll, or die roll, because it's only one die. Die is singular, dice is plural, so another quirk of the English language. So we'll do die roll equals, oh, before we do that, we actually have to create the random object. So let's do that first. Random, random. So random is the class, random is the, with the capital R, and R is the object, the lowercase r is the object, random. And we'll do the new random to create the object and allow us to generate random numbers. Now with die roll, we'll call the random object, lowercase r, and we'll give it a method of next int of 6 and plus 1. Now the reason why we're doing the plus 1 is the next int with a 6 in the parentheses will give us a value between 0 and 5. Well, dies don't start at 0, they start at 1. So we're going to have to add 1 so we can get from 1 to 6. 0 to 5, 2, 1 to 6. And next we'll create a second one, coin flip, equals random, again, of next int of 2. And that will give us a value between 0 and 1. Value between 0 and 1. Well, actually, it's not between 0 and 1. It is either 0 or 1. Since they're integers, there's no decimals, there's no floating point, so we either get the value of 0 or 1, and those are our 2 choices. So, the easy one is the coin flip. We have 2 choices. And the corresponding if statement would have looked something like this. If coin flip equals 0, we can arbitrarily assign tails to 0 and heads to 1. System.out.print line tails else system.out.println heads. Very simple statement. You're either going to get tails or heads depending on the random number. Let's run it. Let's see how that looks. Tails. And if we run it again, we get heads. And again, we get heads. It might be a little more interesting if we put a little more information in here. How about you flipped? And then we can put in the value of coin flip. And then tails. This way you have a little more information of what it was, just to confirm that the value is correct. So let's do the same thing for heads. And we'll put in the coin flip again. heads. And let's run that. Hopefully I didn't make any typos. You'll flip 1 heads. You'll flip 0 tails. You'll flip 1 head, 0 tails, 1 heads. That looks good. Okay, so that looks good. Again, it's a very simple statement. There are only 2 options, 0 or 1. If we wanted to do a switch statement, let's take a look at the syntax for that. Let's jump over into our book, and we'll take a look at the switch statement, which is here in section 10. And I'm going to scroll down a little bit to get a better example. And here's the generic form of a switch statement. So as you can see, we're switching, the command is switch, not if, on an expression. And we are going to list out the different cases that it could be. So in the die roll example, we would have a case for 1, 2, 3, 4, 5, and 6. We would have a default case if nothing else matched. So if there was a scenario where we only wanted to check for a few values and didn't care for the rest, we could use a default. I'll show you what that looks like. Each case ends with a break statement, which is very, very important. If you omit the break statement, the code will continue flowing from whatever case it starts at until it reaches a break statement. So a break statement is critical to isolate the different cases. So let's take a look at one of the examples now. Here is a version for dog age in years with a multi-branch if statement. If dog age is 0, dog age is 1, else 5. So we have it really gets kind of complicated with the else's and the ifs and the else's. Might be a little hard to read. A better way would be able to do a dog age break like this. This is the same logic, but in a switch. So we're switching on dog age in years. Here's case 0. And you notice we have a print and then a break. Then we have case 1 for 1. And then we have a 2 for dog age 2. And then we have 3, 4, 5. And anything after 5, we're just going to go into the default. And you'll notice that each case is broken out by a break at the end. There are no curly brackets other than at the very, very beginning of the switch and at the very end to close out the switch. So it's a little easier to code. So let's see if we can implement this in our example with the coin flip, and then we'll build it out directly for the dice roll. Okay, so jumping back over into our lab, let's implement the coin flip as a switch. So we have the same logic, different method. So let's take a look at switch, and in the expression we're going to put coin flip. Notice that we do not need to do any checking, no comparisons. We're just switching on whatever the value is in coin flip. Now this should bring up some questions for you. Can you do this with a floating point? Can you do this with characters? Well, so remember, cases are distinct and discrete values. So can we do it with characters? Absolutely. Can we do it with integers? Absolutely. Can we do it with floating point? Yes, if we're looking for an exact value. So just keep that in mind. And as a more advanced example, I'll show you some code how we can use a switch statement where the cases are ranges versus distinct values. So there is some advanced functionality in there that we could take a look at that might have some benefit to you. So we'll take a look at that as well. So first, let's finish off the coin flip, and then we'll get to the the die roll, and then we'll get to the grading example, which is the more advanced version. Again, I will save all this code so you can have it as a reference for your labs and for the rest of the semester. So again, opens up with the curly brackets, and we are now ready to put in our cases. So we have our case 1, or case 0 actually. And I am going to put in the tails. And then I'm going to build out case 1, and I'm going to put in the heads. I'm just going to copy the code here, save a little typing, and such. Notice that I do not have a default case here. While it is not strictly required, it's always a good idea to have a default case in case something unusual happens. In this particular test case, we're really not going to have anything unusual. We're going to either have a 0 or a 1. But we'll put it in just for completeness. We'll put in system.out.println, something strange happened, and we could not be here. So that'll be an indicator that, oh, something's not right. We got to take a look at that. So let's run it. I am going to temporarily comment out the if statement so we don't have duplicated output. And now when I run it, you'll see that I have a 0 for the tails, similar to what we had above, a 1 for the heads, again similar, and then we had the default. So let's run it and see what happens. So that's interesting. We flipped 1, we got heads, and that printed properly, but it also printed this. So why did that happen? Well, if you remember, I said each of these needs to end with the break statement, otherwise it will continue flowing down every statement until it ends the switch statement, which could have some benefits depending on what you're trying to implement. Maybe if it did something for 0, you wanted to print that, and you wanted it to print it also for 1. So you could omit the break statement if you wanted to print 2 different things for one roll or one case. But ideally, we want the break statement to keep our cases unique and discrete and the output the way we expect. And there's the first one, the 1 for heads, and the 1 for heads, and the 1 for heads, and the 0 for tails. Okay, good. I was getting worried that something was wrong. So, which one is easier to write and read for 2 cases? Well, I would guess probably the if statement would be a lot easier in this particular scenario. And I guess it depends what you're trying to switch on. Is it a lot of logic for some cases and others? Is it a little bit of logic? That's something for you to decide as the programmer, which way you want to write it. Me personally, I kind of like the switch statement. But maybe you like the if statement. Either way is fine. Use whichever one you'd like. Unless, of course, in the lab or the homeworks or the participation activities specifically ask for one or the other. So always follow the requirements of what you're being asked. Now, let's build out the switch statement for the die flip or die roll over here. And it should be very similar. Switch die roll. And we can, oops, that's not that. We want the curly bracket. And we could do case 1. There is no case 0 because the die starts at 1. And we'll do system.out.println you rolled a die roll. You rolled a 1 and break. Now what if we're using this for some kind of game, some kind of gaming application? And let's say maybe instead of when you roll a 1, maybe you do something like, oh, I don't know, move token 1 space forward. So if you roll a 1, you go forward 1 space. What if you roll a 2? Well, we're definitely going to need the die roll piece. We're going to have that again. Oops, too many tabs. Clean that up. And maybe we want to have a system.out.println move 2 spaces backward. Break. Let's do one more. Case 3. And again, we'll paste in our print statement. And for 3, maybe lose a turn. How about that? We haven't used that one yet. Break. What if we wanted to do something, if you rolled a 4 or 5, you do the same thing? Well, this is where we can be a little clever. we can do case 4, and we can do, again, we can do our print statement. And we could do system.out.println. What do we want to do? Collect 5 points. No, I'm just making it up as I go here. Great. And we'll add a break statement in here for case 4. But what if we wanted to do the same thing for case 5? Do we really want to duplicate all that logic? Well, we can do something like this. If we get case 4, we're not going to do anything specifically for 4, but we're just going to keep executing down until we get to a break statement. So if we do a 4 or a 5, we're going to print either of these two statements regardless. And then we can have a default statement. Let's ignore 6 for now. And the only way it should get to the default is, in fact, if you rolled a 6. Because we accounted for all the other cases. This one's not lined up, it's bugging me. There we go. And we'll do a break statement. So we'll put a print statement in just to have another print statement. Game over. Okay. Temporarily, I am going to comment out the coin flip just so we can focus on the dice roll. So I would expect for every one of these scenarios, we're going to see one or more statements printed. So let's see what happens. Here's our 4. Oh, it's a perfect example for the first try. So, oops, sorry about that. You can see here's our case 4. Gives a little more room. See our case 4, we don't have any specific actions, and we just keep executing down through the cases to code until we get a break statement. So here's a 4, collect 5 points. Let's run it again. Roll the 6, game over. Perfect second test. We got the default statement. Roll the 2, 2 spaces backwards. Roll the 4 again. I want to try to get a 5 this time. Roll the 6. Another 6. Another 6. And there's our 5. Okay. So you see 4 and 5 generated the same output. So this is just a quick little explanation of how we can use a switch statement to break up different discrete activities. Okay, so that was the switch statement. I do want to get onto 2 other topics, so let's jump over to characters. And we did talk about characters a little bit already as a data type, but let's take a look at some operations that we can do with characters. And that is in section 3.12. And we're going to start essentially with this little chart, which is a perfect summary of what we want to look at. But before I do that, let me save our test code so I can post it later into Brightspace for a reference. All right, back to characters. So characters have some operations, and there are some methods as part of the character class, that's this capital C character, that we can use to determine what the character is. Is it a letter? Is it a digit? Is it white space? Or we can convert it to uppercase or lowercase. A typical functions and method naming when we get into that is whenever you have an is in front of it, it usually indicates it's going to return a true or false. So this is going to return a Boolean value. And the prefixing it with TO for 2 usually indicates that it's doing some kind of conversion. So that's good to remember. So when you're looking at the method, you can see, is this a letter? It's going to give you back a true or false. Is this a digit from 0 to 9, a true or false, and then again for white space. So we can look at a couple quick examples of these, and then we'll move on to our final subject, which is floating point comparison. So let's go back to our lab and let's clear it out and reset it to the template. Yes, I'm going to reset it. And once it resets, we'll start implementing some code to test out these different options. So first, let's create a couple of character variables. Letter 1 equals, we'll call that lowercase a. Character letter 2 equals, let's put a digit in there, 0. And character letter 3, and we'll make that a white space. We'll make it just a space. Still a white space, but it's a space. So there we have our 3 characters. Looking at our little chart, we have, let's start with the 2's first, the 2 uppercase, 2 lowercase. I think those are the easiest ones to understand. So let's just do a simple system.out.println. Actually, I'm going to back up a second. Let's create another character. Character, letter, new. And we're not going to assign it a value yet. Let's do letter, new, equals 2 uppercase, letter 1. And one thing that's important to note, whenever we want to do any of these conversions, we have to do this. Character dot to uppercase. And you'll notice that it's a little hard to see, but the font color of 2 uppercase changed to blue, indicating that it's a method that's being used in this character class. And we still need a semicolon. And now we can do our print line. What I was trying to do, I was trying to do too many steps at once, and I wanted to keep it simple in the beginning so we could follow along and make it more complex later. We can print out the original, and we can print out letter 1 and converted, and we can print out the converted value, and we'll see that when I run this, pending any typos, it'll have the lowercase a and the uppercase a. So here we've just used a method to convert a lowercase letter to an uppercase letter. We can also convert the other way, back to lowercase, just instead of to upper to lower. If we try to convert a lowercase letter to a lowercase letter, it still stays as a lowercase letter. That does not change. But what we can also take a look at is these is methods, the is letter, is digit, is white space. And this is where it gets a little interesting. We can do if, we're going to use an if statement. If is letter 1. Notice I'm not comparing it to anything. I'm not comparing it to another letter. I'm not comparing it to another value or another variable. I'm just using is letter 1. And as I keep forgetting to do, character in front of that. And then I'll just put a print statement, print line, letter 1, not in quotes, letter 1, in quotes now, is a letter. So what I'm doing here is in that if statement and the condition or the expression, if statements work on true or false. So if that expression evaluates to true or false, it will do the code in the if. Now, prior to this, we've always done comparisons, where one variable is equal to another, or greater than something else, or equal to another variable. The whole process is doing a comparison and calculating a Boolean value of true or false. In this particular case, the method .isLetter is giving us a Boolean value of true or false. So as long as we know we have a true value there, we're going to do the if statement. Let's run it and see what happens. And I have an extra parentheses. Let's get rid of that, try again. A is a letter. So this evaluates to true. So as long as what's ever in that expression for the if statement evaluates to a true value, whether it's by a method or an expression, the if statement executes. And we can make a similar one. If character dot is number, letter 2, and we can have a similar print statement, which I'm going to copy and paste. Letter 2 is a number. Okay, what does it not like now? It does not like the dot is number. That is very interesting. And that is because it is not is number, it is because it is digit. My mistake. There we go. 0 is a number. What would happen if we did put letter 1 in here? It did not print anything because A, letter 1, is not a digit. It is a number. I'm sorry, it is a letter. So it returned false. And we could do something similar with his white space, but I think you get the point of it at this point. So you have the ability to convert letters from upper to lowercase and vice versa. And you have the ability to check if something is a number, a letter, or a white space. So it could be useful when you're reading your inputs in your labs and you want to see what kind of data you have and take the appropriate action. Okay, so let's save this piece of code. Again, I will post it into Brightspace so you have it as a reference. And now I want to, well, let's do the reset of it, and then I'll jump back into the textbook so we can take a look at the next section. And the third topic, the final topic for this video, will be floating point comparison. And for this one, I'm pretty much going to follow the book because it gives a great example right here. The first participation activity is a great example. When a floating point number is stored in computer memory, it is not an exact value. It's an approximation, and that has to do with how floating point numbers are calculated. Integers are very easy to calculate. You just count the number of bits, and you can make a binary number to make that the appropriate value. Decimal points are a little different, and especially when you have a repeating decimal point like 0.333 and it continues forever. How do you represent a infinitely long decimal in a discrete number of bits? Well, you can't, so you have to use an approximation. So sometimes the approximations don't quite add up right, and when you try to do something simple like this, if you have number of meters is equal to 0.7 and you subtract 0.4 and then you subtract 0.3, we think to ourselves, well, you're subtracting and it should be 0. Well, due to the imprecise nature of floating point, sometimes those values are off, even if it's by such a minuscule amount. It's still not exact. So let's take this code and put it into our test window, and I will explain it. So let me switch it over, and I am going to build it here. So we have num meters equals 0.7, and we have to declare it as a double. And then we'll do some math. Num meters equals num meters minus 0.04. 0.4, sorry about that. And let's just see what happens. Let's put a print statement in, and after each time we change the value of num meters. Num meters, METERS is, and we'll put in the variable num meters. Semicolon, and I'm going to copy that now because we're going to use it in a few places. So we'll run it the first time. Let's see what happens when it runs for 0.7. And I forgot the semicolon. And let's try it again. Nanometers is 0.7. Okay, that was good. Let's put it here and see what happens. And I run it. And there we have our first discrepancy. We should have expected 0.3, but we're not. We're seeing 0.2999, a lot of 9s, and 3. Not exactly 0.3. And if we do the second part, actually I'll just copy these two lines, put it here, change this 4 to a 3. Now I would have expected to be 0. And it's not. It's minus 5.55 times, well, okay, so this notation here, E minus 17, that's the scientific notation. So just put a pin in that. We're going to come back and look at that. I'll do a quick little session right after this piece. So there'll be one more topic, but it'll be super quick. But it's bottom line, it's 17 decimal places to the right, 0.05. So it's a pretty small number. But it's still not 0. So the idea is, if we tried to do a comparison, num meters equals 0.0, and we did a system.printout.println result is 0, and we'll do an else system.out.println the result is not 0. And we'll give it a run. Result is not 0. But clearly, it should be 0. 0.7 minus 0.4 minus 0.3 is 0. So this is where we need to be a little bit smart about it and have to use some additional math library help. So remember, we looked at the absolute value function. We're going to use that. We're going to subtract these values and look at the absolute value, and if it's less than a certain decimal, we can assume, note I said assume, that the value is 0. So, taking a look back at our book, I'll scroll down till I find this statement, and here it is here. This if statement. If the this is body temperature, it's a little different than meters. So if body temp minus 98.6 is less than 0.0001, so this is the precision that we're looking for. If the difference is within, was it ten thousandths of a decimal point, we can assume it's correct. So if we use that over in our meters version, I'm going to comment out this line only, and I'm going to replace it with math.abs. And notice I do not need to import a library, because math is a built-in library. So what are we comparing the absolute value to? We're looking at num meters, and we want to subtract the value we're comparing it to. In this case, it's 0.0. In the other example in the textbook, it was the body temperature of minus 98.6. So we want to see if num meters is equal to 0, we subtract it 2, take the absolute value, and then do a comparison to see if it's less than some digit. And we can do 0.00001. So if it is less than that, we'll assume that the difference is 0. Now, depending on the application and what you're trying to do, maybe more or less precision is required. And that is up to you to decide as the programmer of how close you want to get. So if I run this, let's make sure I have all the parentheses and such in place. It looks like I do. Let's run it. No, I'm missing something. What does it not like? Legal start of type. Okay, I see what's going on. So sometimes the errors are a little cryptic. What we forgot is the opening curly brace. We definitely need that. And now you could see, it kind of highlights it, the opening curly braces, it matches them up. So now we could see it. Now let's give it a try and see how that runs. Come on, there we go, run. Result is 0. The difference is much, much smaller than this, than the 0.001, so we get our result as 0. So that's how we do the floating point comparisons for equality. If we wanted to just see if the number was less than something, you could just do it's less than something. But this is the way you can get around it with the absolute value function. Okay, the final topic, first let me copy and paste this. But the final topic, a brief topic, will be about scientific notation. I'm assuming everybody's seen this by now, either in some algebra classes, either in high school or over at Suffolk, or wherever. Sometimes the easiest websites are the easiest way to explain it. There's this cool website called Math is Fun, and it explains things in a very, very simple way, very straightforward. So I'm just going to use that. And please feel free to bookmark this page. And you know what, maybe I'll even put it as a reference in Brightspace. Has some good information in it and explained in a very easy way. So scientific notation. It's basically a way of taking a very big or very small number, expressing it as a single number with a decimal point times 10 to the power of something. So for this example here they have is 700. 700 is equal to 7 times 10 to the second power in scientific notation. And we're pretty smart. We know 10 to the power of 2 is 100. 7 times 100, okay, that makes sense. So how do we get to 2? Well, you start counting, at least this is the way I do it. You start counting from the ones unit, the decimal point, and you count to the left. 1, 2, and you stop when you have no more leading zero, no leading zero. So the number you have is a whole number, like 1 to 9. So then we have a 7. So it's 7 times, and how many places did we have to move? 2 to the left. So it's 7 times 10 to the 2. This version here is 10 to the 9. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 to the 9, and we stop at the 4. So it's 4.9 times 10 to the 8. 10 to the 9, sorry. It could be 49, we stopped here, right? If we stopped at the 0, 49 times 10 to the 8. But that's not completely accurate. It has to be a number less than 10 on the left side times something to the power of 10 on the right side. So if you count to the left, get a positive, and if you count to the right, which we'll see in a second, you get a negative. So let's go find that negative example down here, and you'll see, where is our negative example? I must have passed it. Well, here's the explanation here, but here is 0.0055. So if we move, now we're moving to the right. So how many places do we count? 1, 2, 3, to get 5.5. So 5.5 is the left half, and 10 to the minus 3, because we counted to the right, so we get a negative number. So that's how we get and can express it in scientific notation. Now in Java, we can't use this x, right? We can't use an x that looks like it's a multiply, so that would be confusing. So what we do in Java is we give it this e exponent, scientific notation, to the minus 17. So this is 10 to the minus 17. So we would have to move the decimal point 17 places to the left and fill it with zeros to make this the number. So you can see it's a very, very small number. Now, the last thing I'll show, if we wanted to assign a value in scientific notation, we can. Example, let's call it example. equals, everybody knows that that we have in that prior example, that 4.9 times 10 to the 9. So we could type it in as 4.9 billion. So 4 billion 900 million, no thousands, no ones. And that's accurate, and it works. But a better way, and maybe an easier way, would be to use scientific notation. And that's the same. So if you see a value being assigned like this, you'll know you'll be using scientific notation. You're not doing some crazy algebra where you're multiplying an e in there. And I'll just run it to make sure that the syntax is correct. And it's not. Oh, because I already defined it. Okay, so this is interesting. So this is an error you will receive if you've already declared a variable and you're trying to declare it again. So it's a safeguard that you can't create two variables with the same name. I'd like to say that was intentional, but it was not. So, okay, there. So it ran. Notice I didn't print anything. It's just showing you that the syntax is the same. So this is how you use scientific notation. So if you see that in your output, you'll know what it means. Okay, that was a rather long video, a little longer than I thought. Anyway, good luck with this. If you have any questions, let me know, and I will see you in the next video.